All right, this section is about transformations. Okay, now there are three types of transformations that you can do with a function. And the first one we're going to talk about is a translation. And a translation moves a function to the left or right and up or down. As an example, let's look at this function, which is, of course, the quadratic function. And what we're going to do is I'm just going to move this function 3 units to the right and 2 units up. And if I take that whole parabola with 3 units to the right and 2 units up, it ends up right here. So the vertex that was at the origin is now 3 units to the right and 2 units up and is now at 3, 2. Okay, now talking about an equation, the equation of this is y equals x squared. This is called a parent function because it's the simplest form. And the translated function will look like this. Okay, and to verify that, let's just plug in x. Let's plug in 3 for x and find out what is y. Now, what it should be is, if x is 3, y should be 2. Is it? Well, let's see here. Plugging in 3 for x, I get 3 minus 3, which is 0, squared plus 2, which is indeed 2. Okay, so it shows that this is the transformed equation. So the equation of a parabola with vertex hk is this. Okay, remember that was our parent function, and this is our transformed function. Okay, so the vertex is at 3, 2. All right. Now what's a little bit weird about this is it's x minus h. Okay, x minus h, but the h here is actually positive 3, so it's x minus 3. Okay, it's not negative 3, so it's x minus a positive h. It's a little bit weird, but that's just the way it is. And then the k is plus k, so plus 2 means 2 up. Okay. So the general equation of a translation then is this. Okay. And the h indicates a horizontal shift h to the right. And a k, in this case, means a vertical shift of k up. All right. Okay, example. Name the parent function of that and describe the translations. Well, and what we want to do is identify the parent function and then describe the horizontal and vertical translations. Okay, the parent function is the cubic function, right? X to the third. Okay. The horizontal translation will be the h. Okay, notice it's x minus 4. So x minus 4. So h is 4. Okay, it's 4 to the right. All right. And then the vertical translation, it's minus 1. Minus 1. So that would be, if it were positive, the shift would be up, but it's negative, so the shift is down. So the shift is 1 down. Example 2. Given the parent function being the square root function, write the equation that has a shift left of 4 and down of 6. Okay, that's the parent function. The transformed function with translations is going to look like this. Okay, we have to identify the h and the k. All right, left 4. Now, if you look back in the previous slide, x minus h would be a shift to the right. So x actually shift to the left here, and the shift down of 6, okay, means that also k will be negative. And the way we're going to work this, I'm going to say we're going to be working backwards. That is, work right to left. So we should identify k first, and k is equal to negative 6, and then h is equal to negative 4 because it's a shift left of 4. Okay, but now when I put this into the equation up here, I have x minus a negative 4. You got to be careful with that. X minus a negative 4 is going to be x plus 4. Okay, and then the k is negative 6, so that's just minus 6. So be careful with the h. The next type of transformation we can do is a scale. Okay, and the scale transformation stretches or shrinks the graph vertically and horizontally, or horizontally. Let's use the quadratic function as a parent function once again, okay, to illustrate how this works. And notice that with the parent function, with the quadratic, if I go over 1, I go up 1. Okay, if x equals 1, 1 squared is 1, so we go up 1. If I go over 2, we go up 4. X equals 2, 2 squared is 4. Okay, so 1, 1, 2, 4. Keep that in mind as we're talking about these stretches and shrinks. Okay. All right. The vertical stretch is going to end up having a 2 times f of x relation. All right. So in this case, we're going to get 2x squared. And what that's going to do to the function is if we're vertically stretching it 2, we're stretching it 2. So whereas before we went over 1 and up 1, now we're going over 1 and up 2. We're stretching that thing vertically. If x is equal to 1, 1 squared is 1 times 2 is 2. So it takes it up to here. It takes it up to 1, 2. Right? So if I went over 2, for the parent function, it would be going over 2 up 4. Here it's going to be going over 2 and up 8, which is off screen. Okay, so it's stretching it vertically. On the other hand, we can have a vertical shrink, and that's going to look like this. Okay, we're going to squash it down a little bit. That's going to end up looking like this. And the function is going to be 1/2 x squared. So that whereas before we went over 1 and up 1, now we're going over 1 but only up 1/2. If x equals 1, 1 squared is 1 times 1/2 is 1/2. Okay, so we're only going up to 1/2. Parent function, if we went up 2, we would go up. Oh, so that point there is going to end up being 1 1/2. Parent function over 2 up 4. Now, if I'm shrinking it to half its value, I'm going over 2 up 2 instead. All right, so it just kind of shrinks that whole function down. All right, now what about horizontal stretches and shrinks? If this is the parent function, a horizontal stretch is going to end up looking like this, f of 1/2 x. Okay, and this is going to stretch it horizontally. It's going to stretch it that way. Now, it might seem weird that that's a 1/2. Mr. Tautges, why isn't that a 2? Well, it turns out to be a 1/2. We got to keep that straight. Note, if we go over 1 up 1 for the parent function, now we're going over 2 and up 1. All right, so if x is 2, 1/2 of 2 is 1, squared is 1. Okay, so stretching it out horizontally, we actually put a 1/2 in there. Seems kind of weird, but that's the way it is. A horizontal shrink is going to end up looking like this. Okay, so there's a 2 in there, 2x. And that's going to make the function do this. It's going to shrink it down horizontally. It's going to squeeze it. Okay, and so we get 2x squared. So once again, whereas before we went over 1 up 1, now we're only going over 1/2 and then up 1. We're squeezing it horizontally. Okay, if x is 1/2, 2 times 1/2 is 1. Squared is 1, so we get it there. Okay, so seems kind of weird, but with the horizontal stretches, we put a 1/2 in there. For the horizontal shrink, you put a 2 in there. Seems kind of backwards, but that's the way it works. So this is the general form for a scale. I have the A and B in there. All right, the H and the K are there. Those are the translations. But A and B are the stretches and shrinks. If the coefficient is in the front of the entire function, it is a vertical stretch or shrink. If the coefficient is in front of only within the x within the function, if the coefficient is x only, then it's a horizontal stretch or shrink. Okay? All right, another example. Let's describe the scale of this. Okay? Now, we have a 3 there, so it's either a vertical stretch of 3 or a horizontal shrink by 3. Remember, the horizontal shrink is kind of backwards, right? So which one is it? Well, it's in front of the entire function, in front of the entire x to the third. Okay? There's no parentheses involved, so it's in front of the entire function, so that makes it a vertical stretch. Okay? How about this one? Okay, we have the absolute value function, and there's a 2 there. Is it a vertical stretch or is it a horizontal shrink of 2? Well, this time the 2 is within the function. If it were out front, it would be different, but here it's within the absolute value function, and that makes it a horizontal shrink of 2. If the 2 were out front, so it's 2 times the absolute value, blah, 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 then it would be vertical, but it's within the function itself, so it makes it horizontal. All right, next example. Given the quadratic parent function, write the function with a vertical stretch of 5, horizontal stretch of 3, vertical shift down of 4. All right, in general, the function is going to look like this. We have to identify the a, the b, and the h, and the k. All right, and I'm going to say, let's work backwards. Let's analyze the shifts first, and then the shrinks. So I'm going to say work backwards. Get k first, then h, then b, then a. All right, now the k is the vertical shift, and here we have vertical shift of down 4. That makes k negative 4. All right, horizontal horizontal shift. I don't see a horizontal shift, so that means h is 0. Okay, then we have now we got to get the b, the horizontal stretch or shrink. It says a horizontal stretch of 3. Okay, so that means that b, it's kind of backwards, that means that b is going to be 1/3. Okay. And then finally, a, which is a vertical stretch, has a vertical stretch of 5, and so that means that a is equal to 5. Okay, so identifying all the quantities, and then we can just insert them into the general function above, and we get this. And there's our answer. Okay. Now, note, there was no horizontal shift, so I said h is equal to 0. If it turns out that there's no vertical or horizontal stretch, okay, if there's no stretches involved, then we have to set a and b equal to something, but we don't set it equal to 0 because that would make the x term disappear. And that doesn't make sense, right? Because we need it in there somewhere. So a and b are never 0. If they're not involved in the problem, set them equal to 1. If the shifts, if h and k are not involved, if there's no shifts, set those equal to 0. But if the stretches and shrinks are not involved, set a and b equal to 1. Okay, let's do this example. Given that parent function, write with these parameters. Okay, the general form of such a function is going to look like this. And we have to identify the a, the b, the h, and the k. And once again, we're going to work backwards. Okay, we're going to do the shifts first, and then the stretches or shrinks. So let's see, k, it has a vertical shift up 4, so that means k is 4. Okay. H, the horizontal shift right 5, that means that h is 5. A horizontal shrink of 1/2, it's kind of backwards with the b, so b is equal to 2. And then a vertical stretch of 2, so that means a is 2. Okay. And then we can insert the values into the general form of the function, and we get this as our answer. All right, on to the last translation, and that's a reflection. And the reflection involved the axes, so that the x and y axes are mirrors. Okay, across the x-axis, it will be a vertical reflection. Okay, and under that condition, the y, you put a negative sign out in front of the f of x. Okay, as an example, we can use this function x squared is equal to 1, x squared plus 1, and just put a negative sign out there, and that just takes all the values that were above the x-axis and it moves them below the x-axis. So it just reflects it across the x-axis. So just put a negative sign out in front of the function. That takes the positives to negatives, and vice versa. Across the y-axis is going to be a horizontal reflection. And under those conditions, we're going to have y is equal to f of negative x. The negative is now inside the parentheses. As an example, take this function, x plus 2 quantity cubed, which is a cubic function that's shifted to the left by 2 units. By putting a negative sign in there, it just takes it to the opposite side of the y-axis. Okay, so whereas the point here is negative 2, 0, which I get by plugging negative 2 in for x, negative 2, 0, here the reflected is negative 2, where x is positive 2. If x is positive 2, we get negative 2 plus 2, which is also equal to 0. Okay, so it just reflects it across the y-axis. Okay, example. Describe these reflections. So This is either a vertical reflection or a horizontal reflection. And the key is, where's the negative sign? Where's the negative sign? The negative sign is in front of the entire function. And that makes it a vertical reflection. Okay? Now, what about this example? Here, we have the negative sign in front of the x within the function. In fact, we could write this inside the parentheses. We could write that as negative x plus 4. So the negative sign is within the parenthesis. The negative sign is within the parentheses. And that makes it a horizontal reflection. All right. Given the parent function, the square root function, write this function with these parameters. The general form is going to look like this. Once again, we're going to work our way backwards. And so we're going to do the shifts first, then the stretches and the shrinks, and then the reflections. Okay, do it in this order. So let's see, K is a vertical shift, and there is no vertical shift, so K is equal to 0. Horizontal shift, right 4, that makes H equal 5. A horizontal stretch, there is no horizontal stretch, so B is equal to 1. Vertical stretch, oh, there's a vertical stretch of 2, so that means A is 2. Okay, and so inserting it into this, we would get that. Now the reflection, it's reflected across the x-axis. That's a vertical reflection. Okay, in a vertical reflection, we just put a negative sign right out in front of the entire function, and there's our final answer. All right, what about this? So we have the absolute value function. In general, it's going to look like this. Okay, and now we have to analyze all the stuff, and then we're going to once again do the shifts first, then the stretch shrinks, and then the reflections. So let's see, K. I don't see a vertical shift, so that means K is equal to 0. Horizontal shift, right 5. Okay, so that means H is equal to 5. Horizontal stretch, I don't see a horizontal stretch. Vertical stretch, there's no vertical stretch either, or shrink, so A is equal to 1. And so inserting it into our general form, we would get this. But then it's reflected across the y-axis, so that involves putting a negative sign within the parentheses, so make x negative x. And there's your answer. All right, now we're given an equation. We're given a graph, and we want to find the equation of this. Okay. All right, so once again, we're going to do the shifts first. All right, so the vertex has been shifted over 3 and down 1. All right, down 1. So that makes K. So the new vertex is at 3, negative 1. So K is negative 1, and H is 3. Okay, now let's look at the shifts. Okay, so the parent function going over 1, or the stretches and shrinks. We did the shifts. So stretches and shrinks, parent function over 1, up 1. What does our function here do? It also goes over 1 and changes by 1. It's down. There's a reflection. We'll deal with that later. But 1, 1. So it doesn't stretch vertically, nor does it reflect horizontally, because 1, 1, 1, 1. Okay, nothing changes. So there are no vertical or horizontal stretches or shrinks. That's nice. So A is equal to 1 and B is equal to 1. So then in our general form, okay, now we can insert our numbers, and we get that. And now let's deal with a reflection. It's a vertical reflection across the axis. And for a vertical reflection, we put a negative sign out in front of the entire thing. And so we get this. Okay. Now, note, you can always test your answer by taking a point on the transformed parabola and see if it obeys this equation. I'm not going to take the vertex. I'm going to take a different one. I want to take 2, negative 2, this point right here. 2, negative 2. If I plug 2 in for x, if 2 is your input, you should get negative 2 as an output. Let's see if we do. Let's put 2 in for x. 2 minus 3 is negative 1. Negative 1 squared is positive 1. That makes it a negative 1. And then negative 1 minus 1 is indeed negative 2. Okay? Just for fun, we could test a different point, like 4, negative 2, or something else. So you can always use a point on your transformed function, or your transformed graph. Your function that you come up with as an answer should match with the graph. So use a point on the graph, test it with your equation. All right? So you can verify your results. All right, as a final example, we want to sketch the graph. Last time we got an equation from a graph. This time we're going to get a graph from an equation. Okay, so this is a cubic function. So the parent function is going to look like this. I want to have it as a reference. Okay, and the general form of that is going to be this. And so now first we analyze the shifts. Okay, now the new vertex. Okay, find a new origin, right? The new origin. And we can see it has a horizontal shift, negative 1, 1 to the left, okay, and 3 down. So our new origin, h of k, is now negative 1, negative 3. So our new origin is going to be at negative 1, negative 3. And that changes the axes. So now we have a new set of axes. I can move the y-axis 1 unit to the left, and the x-axis down 3. And that puts the new origin right here. The origin is a part of this graph. Okay, so we find the new origin. All right, then we deal with the vertical and horizontal stretch or shrink. Now, it says here, according to this, it has a vertical stretch of 2. So what does that mean? The original function goes over 1 and up 1. But with a vertical stretch of 2, it's going to go over 1 but up 2. So the point would be there. Okay, to the left, over 1, down 1 would be over 1, down 2. Right there. Okay. Okay, finally, we're not quite done because there's a negative sign in there, and so that means that there's a reflection. And the reflection is across the x-axis because the negative sign is out front. So that's going to take all the points that were above the new x-axis, and it's going to move it below. It's going to move all the points that were below above. So it's going to shift those points to here. And that's going to be our transformed function. Okay? All right. Now, let's see if our graph is right by testing a point. So I have a point right here. Negative 2, negative 1. Negative 2, negative 1 should satisfy this equation. So if I have an input of negative 2, I should get an output of negative 1. Let's see if I do. All right. Negative 2 is x, right? Negative 2 plus 1, that's negative 1. Negative 1 cubed is negative 1. Times negative 2 is positive 2. And then 2 minus 3 is negative 1. So this point does indeed satisfy that equation. So once again, you can test your results. After you get your graph, pick a point on that graph, take the coordinates, insert them into the original equation, and the left side should equal the right side. If it does, pretty good chances that your graph is correct. So you have a chance to test your answers. So you can verify them, which is always nice. All right, so those are transformations. We have translations that move it left, right, up, or down. We have stretches or shrinks that can either stretch it, shrink, squash it, make it skinny, whatever. And then we can also reflect it across the x and y axis. So transformations. Work your way backwards. Do the shifts first, then the stretches and the shrinks, and then deal with the reflections, if any. Okay? All right. Practice problem time.